analytically, because now we have our integrals. You can also get it with some kind of integration by parts of the correlators. And then you will get the Schwinger-Dyson equations, but it's actually exactly the same that you get combinatorially. And this is what you use to later produce the topological recursion. So we will start with the combinatorial part. So the idea is that we want to build bijections of different sets of maps. So we want to take our maps and remove the first edge of the first boundary and see which are all the possibilities. So we will build some bijections that will translate algebraically into some relations between the generating series. Okay, this is the idea of what the touch recursion does. I'm calling it touch recursion because this method was originally invented by Tat in the 60s, and that's how he solved the planar case. But actually, he never did higher genus. Okay. So I want to start with this guy. This is the generating series of maps with fixed length and genus G. So I want to take any map. And this is the first boundary. Yes, I took the convention that the boundary sits on the left of the root. So this is okay, this is the first boundary. And now we want to separate all the possible cases of what is this guy. So the first guy, in the first case that we will treat, this will be just an interior face of length G. So we can call it Jagon. I was calling them yesterday. And you remove it. We find something. So what has changed from here? Here we had a boundary of length L1. And now this goes to a boundary of length L1 plus J, so something that is longer because we have added this, plus J minus 2. The minus 2 is because I removed this guy. And remember that I'm counting half edges, so I'm actually removing 2. And also there is a canonical way of rooting the new guy, let's say. So we should just take a convention. So we can just say that is the previous one in the boundary, okay? But you can take any convention, it will work. So okay, this tells us that this generating series will be equal to the corresponding term. So I want to sum, why am I putting a minus? We want to sum over all possible lengths of this Jagon. Okay, so actually here I took my old convention, not the convention from yesterday. I will try to fix it on the way. So what I'm saying is that I was only allowing these Jagons to be of length from 3 to D yesterday, if you remember. This is not how I wrote it down in my notes, but it should be fine, hopefully. So here we obtain something that has one less Jagon, that's why I'm adding this T, and that has length L1 plus J minus 2. And it has the same genus. So, okay, it's equal to all these possibilities plus, and then we have to figure out if there are other possibilities here. You can probably imagine that there are many more possibilities. Well, not many. Don't be scared. Actually, there are 3 more possibilities, depending on what you define as possibility. This Schwinger. or if you pronounce it in the English way, Schwinger, I guess. Okay. Okay, then the next possibility is quite similar to this one. But we want that this is also a boundary now, because just because this is another possibility, right? So this is a boundary of length L1. Okay, let me denote of length L1 with an arrow. And this is another boundary. So we need to say which one, because, okay, this is always the first one, but this one can be any. So it's a boundary of length Li for I different from 1. Now if we remove it, so this time I didn't draw any genus, but there could be genus, there could be anything. We remove it, we get something very similar as before. We just get that the first boundary now has length, again, L1 minus, plus Li minus 2. Okay? And then we also take the convention that we mark the previous one, but we also forget which one was marked in here. And this is important for the algebraic relation that we get. So this plus now goes here. We just need to add all the possible boundaries from 2 to n. And then we multiply by Li, and this tells us where this was marked. And we just put what we need to put. Okay, sorry. This has first L1 plus Li minus 2. And and then, of course, we want it to have the same number of boundaries, minus 1. So the Li is not there anymore. Okay? Is this clear? Are there problems? No. Okay. Then another possibility I will do here. These two last possibilities will give us the terms that already look a little bit like the topological recursion terms. You can already recognize them because you already saw the formula of the topological recursion. So we have something like this. This is the first boundary. If we remove this guy, we get an extra boundary because this guy gets disconnected. And we reduce the genus by 1. Okay, this is the case in which these two guys are connected. Okay, so we just get this thing. And again, there is a canonical way of marking the new two boundaries. So there is no problem in this for our bisection. Now this has genus G minus 1. Okay, so this goes from n boundaries of lengths L1 and some other else. This is the tuple of the other boundaries, the tuple of the length of the other boundaries. And then here we will have n plus 1 boundaries of length. Okay. J, so J could be anything. L1 minus J minus 2, so this is the two things for here, so they have to add up to L1 minus 2, okay, because we just removed two half edges, and the rest stays the same. And then algebraically, this gives us the following type of terms. In which one? In number 2? Oh, this is number 3. Yeah, this guy, you have to count it twice. So, okay, if you sum all this length and all this length, and then you remove this, you are removing this twice.
So that has length 1 in your picture. The arrow from...
So it has length 1 on one side and length 1 on the other side.
Okay.
So if you sum these two lengths, you will have the sum of the lengths minus 2. Okay. And actually the idea of the minus 2 is the same in every picture. Okay, and then I have to write the generating series that corresponds to this, right? So maybe let's do it like this. The 3 for the touch recursion in the generating series is just the sum for all possible j's until L minus 2. And then it has to have a boundary of length j, another boundary of length L1 minus j minus 2. We just put them, the two of them at the beginning, why not? And then the rest of the boundaries stay the same. And the genus is reduced by 1. Okay. Then let's do the fourth type of term. And yeah, actually, this guy we will need it. This sum we will need it for the next thing as well. So I remove the parentheses, but don't get stressed. There are things coming. So the other possibility is the disconnected case. It's the same, but in which the result is disconnected. Sorry that I'm losing some artistic motivation, but probably by this point you can guess very well. Okay, so in this case we had a genus, and we had some, what am I labeling? Some boundaries in here, labeled by a set I, and another set here j. And then here we will have a new thing that has a genus g minus 8 and 8. And h goes from 0 to g. Okay, why am I drawing genus? I don't know. Then this one has n boundaries of length L1 and the set L. And this one has 1 because of this one, plus the cardinality of I boundaries. And this one has 1 plus the cardinality of j boundaries. That's it. So in total, we will have n plus 1 boundaries. And these boundaries have lengths j I. So I is the tuple of the length of these boundaries. And here we will have lengths L1 minus j minus 2 and the tuple j. Okay? So this corresponds, and this is the term number 4, to this sum. So we sum over h from 0 to t, and then we sum over all possible i's inside L, and we have maps with one extra boundary of length j, and the rest of the boundaries stay the same. Oh, sorry, this is not L, this is I, of course. Okay, so now this is the generating series for just this component. Okay, we are in the disconnected case, so that's why we will get a product, as in the topological recursion formula. And this guy has length L1 minus j minus 2, and the rest stays the same, which is L minus I. This is equal to j. Okay, and then the genus, oh, and this is wrong, sorry. We need to distribute the genus, as I said. Oh, and I did it the other way around. So this is g minus 8, and this is 8. Okay, and this closes this parenthesis, because here I was summing from all possible, so for all possibilities of j, and I still have to do it here. Are there questions?
I'm just trying to imagine like low-dimensional cases where
That's a good idea.
to understand.
So okay, I'll let you reflect a little bit while I erase this. So now we have our complete touch recursion, at least at the level of the f's. Yes?
Can you explain again in the contribution to the factor Li?
This Li? Yes, that's a tricky one. So to go from here to here, I kept saying that when we erase this one, we are erasing the root, and we want our map to still have a first boundary. So we root it in a canonical way. So we don't have to take into account that in the bijection, because it's taken care of. But this other boundary, in this case, is not. We don't remember where this was marked. So we need to multiply by all the possibilities of marking the other face that is on the other side.
And so every time you shade, that means that is a disk in your complement. Thank you.
Yes.
So.
Yes.
So, for example, in the first picture, that means that actually the shaded part is a sphere, and then you put something else.
Exactly.
And similarly, like, for example, in number 3, that means that you have a sphere in the shaded bit, and so you have like a genus, and you're like, yeah, decreasing the genus. So
yes,
like
this is a good question, because here you have to imagine that the whiteboard is
closed.
the
yes.
sphere. So okay, but in here you get two spheres.
Right.
Otherwise, it doesn't have the right topology.
Right.
This guy, and we want it to have the topology of the disk. So
Okay.
this is what happens here, and also here you have two spheres. So you have two different maps disconnected. That's why you get the product.
Okay.
So yeah, exactly.
And the I and j are just counting the number of roots that you have, the number of marked
Exactly.
edges, yes?
Exactly. It's the tuple of lengths of the other boundaries that are not the first one. So these are
Okay.
the first cardinality of I ones, and these are the rest.
Okay, thank you.
Okay. More questions? No? Okay, so now I gave you how the touch recursion looks like when we fix the lengths. But we are actually interested in letting the lengths be anything. So we want to sum overall possible lengths, multiply by the denominators with the x's, if you remember from yesterday, to build our correlators, and then see what we get at the level of these w's, okay? And this formula, I will write it directly.
Excuse me, Elba.
Yes?
I will probably annoy you a little bit, but this recursion is valid only if the LIs are large enough to only if you can remove an edge. So where initial position.
Yes, I'm hiding some little details, yes. So you can figure those by yourself, maybe tomorrow if you want. Yes, but those are easy. You just have to think of them apart.
In number 3, can you say again what the L minus 2 on the top of the sum is? Like what's L with no index?
Sorry, I'm not hearing you very
Huh.
well.
On top
In
of
sum
the-
3?
This one?
Mm. Yeah.
It's probably an L1.
Yes, because remember that when we sum these two guys, they can be at most L1 minus 2.
So this is L1 in the equation. L minus 2.
Yes. This is your question. Okay, yes, sorry. L1 minus 2, yes. Okay, very good. You are very sharp with the details, so that means that you're understanding. So let me now write what happens at the level of the correlators. So we actually want to apply an operator that looks like this. Just taking the sum over all possible lengths. Let's say, well, we can say 0, but we said yesterday that that case is almost trivial. And then we put something in here, and we just put the right denominator that keeps track of the lengths of the boundaries. So we want to apply this guy to all our equations. If we apply it to the first term, the one on the left-hand side, we just find our correlator multiplied by x1, okay? This you have to remember from yesterday, the definition of the WGN. That was just exactly the application of this operator. Okay, this is what is in the left-hand side. But now I will put more stuff to make my life easier. So I will also want to put, okay, let's try like this. This you can check all the details. There are some terms that are a bit difficult, so I don't expect people who have never done it to see them directly. I will just leave that as a work for you to complete. So this whole guy is now v prime of x1 times w g n x1 xn. So I should probably remember what v is. I have to have a bit of patience because I'm not even writing the equality yet, but it will be there. I'm just writing in the way that it will be easier for me to manipulate afterwards, otherwise I have to write it many times, and it takes a lot of time. And so yeah, I remind you what this v is. So v prime directly. So v prime is just x minus. Yeah, now I'm mixing the notation from yesterday. Did I make? No, I made it already correctly. Okay. X to the j minus 1. Okay? If you remember, yesterday I defined the potential. This is just the derivative of the potential, so you can remember. Yes. Okay. So you can observe that here we just this equality is true. So if you are checking this term just from this guy, you will observe that in that term there are too many things. Okay? Because remember that in the W's, everything is in the denominator. You don't have anything that is of positive exponent in x. So in here this can happen, right? Because this just starts with 1 over x1. So it can be that this guy is bigger, and then it will give positive things. So we want to remove this to get the right thing. And when we remove this, we call this p from polynomial, because this is just a polynomial, and this is quite important. And this polynomial is just what I said, removing the right thing, which is just removing from this guy the things that are positive in x1. Okay, and denote it like that. Very good, and now I will put my equality. Okay, so far I did until here. I just put this guy on the other side and did these little manipulations. So it's good, I can erase this one already. So on the other side, I will just put this one, and this one, I guess you will not understand why I get this thing, because this one is a bit complicated. But I just leave it as an exercise to not lose time with something that is just some combinatorics. Or maybe if you are used to these things, you will see immediately why you get this type of thing. But when I was learning this, for me this was substantially the worst term. So don't be too scared. So now I need to tell you what to put in here. I just write it downstairs. Oh, well. This guy is just the same guy, just without the x1. Okay? So this just comes from number 2. And then I put the other two terms, and these ones are very easy to get, so you can think of them while I write. We just need to put topology, the right topology, g minus 1, n plus 1. And then the same variable, we. Because this came from the same boundary. That's why. And then the rest. And the last one, you need to sum over all possible topologies. This is what we were doing here. And then when you add the x's in the denominator, you can see that you can arrange them in a nice way. So it just gives you the product of the correlators with the split topologies, let's say. So something that looks very similar to the terms in topological recursion. Okay, now these guys are just a partition in 2 of the x's, of the set of x's. And then this just has g minus 8, yes? 1 plus I boundaries. It's just x1 and I. And on the other one, we have 8, 1 plus j, cardinality of j, and x1, j. Okay, and we are done. This is our final touch recursion. Are there questions? Okay, so now we want to solve this. And topological recursion was not the first, we want to solve this recursively in the topology, right? So we will first solve it for 0, 1. And this will give us the spectral curve. And this was not done for the first time by topological recursion. But the method of topological recursion has even very nice things for this very classical problem. So there are various things. One is that we will go from this recursion that was already before, from a recursion, from the topological recursion that has many less terms, okay? We will only see in the end 3 and 4, as you can imagine. So if you want to see properties of your maps, for example, if you are doing like critical exponents of maps or something like that, it's very nice to get rid of all these other nasty terms because you don't have to take care of those with topological recursion. That is one nice thing. The other thing is that whatever you will check for your problem that you care about, if you do it with topological recursion, you will probably get something that is more universal. For example, again, if you do this study of behavior of criticalities directly with the formula of topological recursion, you will probably be able to apply it to other problems because the method is universal and it works in many cases. And apart from that, it gives a very nice explanation of something that is called the rationality scheme in combinatorics. And I will tell more about that later. I'm just saying this little comment for the experts in maps. So should I start with disks? Maybe here, this is fine. So now we will solve for disks, and we want to find our spectral curve, so we will also solve for cylinders. And finally, we want to find the formula of topological recursion. So how to do that? This can be called part 4, I think. And sorry that I'm using the same type of things. Maybe I can call it square here. And I should maybe change pen. Okay. He didn't like it. Okay. So now we do disks. So we just write our touch recursion for the case Gn equal to 0, Gn equal to 0, 1, sorry. And we find the following thing. We find that there is a polynomial relation between x and W01 of x. So this will just give us the spectral curve. So this tells us first nice thing, and is that the generating series of disks is algebraic, actually. So because remember that this is a formal power series. So we just proved that it's algebraic because this is a polynomial. So this is very nice because actually we kind of transformed a problem that had infinitely many unknowns into a new problem that has only finitely many unknowns, which is finding this P01. If we find P01, we compute it, omega W01. Okay, so let's do this. This is very easy. This is just the formula from high school. To solve a quadratic equation. Okay, first observation, we have two branches as a solution, but we want to take this one. Why? Well, because right now it's the only one that gives us a hope that this can work. Because remember that this starts when x is large. I mean, the definition of this guy, you can see that this starts with u over x. U was the parameter that was keeping track of the vertices. So this is the first guy. And if we don't pick the minus, we will never be able to kill the leading terms in this polynomial in here. Why? Because maybe it's not, maybe it was not super clear from what I said, but if you see the definition of P, P01 is this guy over here. This one starts with U over X. So this one will have, so the whole thing will have degree, at most, the degree of this guy minus 1. Okay? And the degree of V prime is D, by the way, is D minus 1. Sorry, D was the degree of V. Yes, so I was saying that the degree of P01 is at most D minus 2. So it will never kill this guy if we pick the plus. If we pick the minus, we manage to find a solution. But we don't know much more right now. So okay, what can we do? For the moment, this guy was just a formal power series in X. And then we said that it's algebraic, okay. But can we do something more? Well, actually we can. We know that this guy is well defined around infinity. But we can actually analytically continue it. And it's not so bad. It just has some square root in here. So what is the worst that can happen? Actually, if we just take the roots of this polynomial in here, this guy has degree 2D minus 2. And we just expand it. We call the roots AI. So this guy has degree 2D minus 2. Then the worst that can happen is that we have cuts going from one of these zeros to the other. Okay? So we have these cuts, but in the rest of the plane, this is okay. So if we want to analytically continue the omega to the whole plane, it will not be okay. It will be multi-valued. We cannot analytically continue to the whole plane. But we can analytically continue to a lot of plane, so we should just avoid these cuts that come from the square root, okay? It would take some time to see the exact structure, but probably you saw these things in many occasions in other cases, so it doesn't sound too unreasonable. And now we want to see what happens exactly, and what happens is even better than that. That is the worst scenario that we have now, that is not so bad. And then what actually happens is even better. So what we do is, okay, now our object is multi-valued in here, in the whole plane, but we want to find a cover in which it's not multi-valued. So this is what we do. We define a Riemann surface that it will be a cover of that one. Just as the zeros of our polynomial. Well, we may need to compactify it. This will be a cover of CP1, and this will be our X. Okay? So one little remark is that if the number of cuts is the worst that can be, that is D minus 1, then the genus of this Riemann surface would be at most D minus 2. Okay? And this just very intuitively, what happens is that we are taking a double cover, that is this Riemann surface. So for example, if it has 3 cuts, the genus will be 2. Okay, just for you to have an intuitive idea of what's happening. This is a ramified double cover of the Riemann sphere. Okay. So now let's study more what happens. The next thing that one needs to prove, I will not prove it actually, because it's a bit technical and doesn't give too much at this stage, I would say. But what we need to prove is that there is actually only one cut. This is what often in physics people call the one cut assumption, but it's actually not an assumption. It's something that you can prove. And apparently in combinatorics it was sometimes called Brown's lemma. So what this tells us, one cut slash Brown's lemma, is that actually the discriminant only has two poles that are two zeros that are simple, and the rest are just paired, 2 by 2. And this eliminates all the cuts except one. So this is just of the following shape. Sorry, there is a 4 in here. I didn't write the 4. Sorry. So there exists an m that is this big factor to the square, and then the two simple zeros that we call a plus, a minus. So actually all these cuts are not there, and this will be a plus, a minus. And then we can write a plus and minus as some alpha, well, this expression with some alpha and some gamma. And these guys are just power series. Actually, not in this formalism. They are just polynomials. No, are they polynomials? Well, they are at worst power series in the T's. But maybe they are polynomials in the T's and power series in the U? Yes, okay. Yes, usually I just get rid of the U and do the more general case in which you also include these phases of length 1 and 2, and then you have to treat it a bit differently, but this case is a bit better, a bit less technical. So it is just a power series in U, which is the variable for the vertices, and polynomial in the T's. Okay. So now we have our guy omega 0, 1 that looks like this. We have shown actually with the lemma that our Riemann surface has genus 0. So it has to have a rational parametrization. And you can actually find a very nice one that allows you to write this just as a rational function. And then this is very, very nice because we turn our algebraic function into now a rational function. So for this we need a new variable, and this is what is given by the x. Now our z, our new coordinate, lives in the Riemann sphere. Okay? So what we call y is just the rest of the W01. And this is a rational function of z, and you can actually show that it has this shape. It takes just little work, but I'm not doing the details of why this is of this shape. And this is the spectral curve of this case. So, okay, important things. Now we showed that with this parameterization, this is a rational function in Z. With this parameterization, this is actually just something very easy in Z, and that's why this turns this into a rational function. Okay? And this is what I was saying before that is important in combinatorics. This is what is called the rationality scheme. And actually, this alpha and gamma have a combinatorial interpretation that I will not be able to explain, but it's a nice combinatorial interpretation in terms of mobiles, that are these things that are in bijection with maps and that are extremely useful. So this type of structures suggest something very rich at the level of combinatorics. They suggest that these complicated maps are actually built of smaller pieces that we can control very well. And well, this has to do with this combinatorial interpretation that I'm putting under the carpet. But it's very nice that our generating series is a rational function in this variable that we understand in this way. And the good thing of topological recursion is that it gives you for free, if you prove that your problem satisfies topological recursion, it gives you for free that this happens for any topology. This is not something easy to prove at all just with combinatorial tools, I would say. So this is something nice. So okay, let's describe a little bit more the spectral curve so we can work. So okay, maybe I should do the picture of the transformation. So what this has done is opening the cut, doubling our thing, and sending the exterior of the cut to the interior in here. It sends the A minus to -1, the A plus to 1, and well, it has doubled the thing. Maybe it's easier to see if I draw it like this. Okay, this was our guy that like this one, but it's of genus 0 because we showed that there is only one cut. So these are spheres, they are 3-dimensional. And then here we have opened the cut. So this has turned into this double cover. Okay, here we have sigma plus, sigma minus, and this is sigma plus and sigma minus represented in here. Yeah. So this is the idea of what the X does. Then we should compute the ramification points. Okay, they are easy, but there are two of them. We just get 1 minus 1 over z squared equal to 0. And they are just plus and minus 1. Okay. And what else do we need? We need the involution around each ramification point. Well, in this case, it's very easy. And it's even a global involution. We can just send z to 1 over z. The x stays the same. So the involution is just 1 over z. So, okay, remember that what happens locally is that around each ramification point, the x looks like a square root. A is our ramification point, or maybe let's call it R, because A had to do with the cuts, and it has nothing to do with that, or, well, little. And around the ramification point, we have these two preimmunities of every point that go to the same z, to the same x, sorry. Okay? This you probably understood already quite well from Bertrand's lecture, because this is what happens in general for the classical topological recursion. So, okay, I will say very little about cylinders, but cylinders are very nice. because here we are in topology 0, 2, and it's where we get the Bergman kernel, which is the universal object. So the very cool thing is that the generating series in the Zs that we found is universal. So what do we mean by this? We mean, well, you already saw a lot of why this object is nice in Bertrand's lecture. But at the level of maps, at least, the very nice thing is that this guy looks the same for any type of maps, any type of internal structure. Even for many maps with decorations, you see the same object in the sets. Something that is very simple, that is attached to just the Riemann surface that we got as a cover, which in this case is just CP1, so it's the simplest possible Bergman kernel. So it's independent of the T's. It just looks completely magical that you can get maps out of this so simple object. So okay, now I'm writing xi as x of zi with I 1 and 2. And we just get, we need to add this shift that may look a bit mysterious at the beginning, but it's just something that we need and doesn't contribute at all at the level of combinatorics. But with that, we get the Bergman kernel here. So I don't know if this was denoted B in Bertrand's lectures, maybe. That is the same Bergman kernel as for many problems, as for the Airy curve, for many things. And it's just because the spectral curve is of genus 0. So we just get that one, and it's the fundamental differential of the second kind on CP1.
Excuse me, Elba. So far, did you put a dx1, dx2 in the definition of W02?
Sorry?
Was there a dx1, dx2 in your general?
No. Yeah, thank you. This is very good. This is a mistake. The dx1, dx2 should be multiplying the W02 because the W02 is a function and we want it to be a differential. Thank you. Yeah, I was just wondering if I wanted to say something else. So yeah, this is very nice because usually this happens for many, many problems, as I was saying. You put here your combinatorial thing, you add this shift that does nothing combinatorially, and you always get the same thing. So from the same thing, if you know the x, you can now get many different numbers for topology 0, 2, just from the same type of object. Okay, so I will not say more about this because Bertrand already said a lot about the general Bergman kernel. And by the way, this is something that you need to prove. It's not trivial at all that this is true. You need to prove it also using touch recursion. But I will skip that thing because I think it's better if we see the details of the stable topologies. Well, maybe I will skip that. Because with this you can learn a lot of particular tricks for a specific case, but that are useful in any case of topological recursion. Higher or stable topologies. Okay, so what happens here? We already hinted in here that the natural objects are not functions, they are differentials. So let's define them in general, even if you already saw them, and you can maybe guess them for higher GNN, but I will write them here. So for any GNN, the natural objects are defined on sigma, so on the cover, and they are what we call the omega GNs, and they are equal to WGNs of x1, xn. Again, I'm using that the xi is x of zi now, because now we know what x is. So I can do this, multiplied by dx1, dxn. And then for base topologies, we need these little shifts. This one is this guy in here. Yes? But turned into a differential, and then we need the shift for 0, 2 that I just talked about. Are there questions, by the way? Maybe it's been a long time. I don't ask for questions. Good. Yes, so now I will state some things that you can get from touch recursion, and that I will use to prove the topological recursion. So touch recursion implies that the omega g ends are symmetric. They are symmetric meromorphic differentials. That they are skew symmetric. This you can get by induction on the topologies. I will not do it, but it's easy. You can again get it from the recursion. Yeah, I already said that. Okay, what do I mean by skew symmetric? I just mean that if we change this to the guy with the omega, we just get a minus sign. And well, this is just 1 over Z1 in this case. And the last thing is the pole structure. But you also have to believe me that it's not difficult to prove from the recursion, and maybe this you already saw in general in Bertrand's lecture for some cases. So you can imagine that. I think you saw it in Bertrand's lecture for loop equations in general. This is a particular case, so it should be the same type of technique. So for stable topology, so for 2g minus 2 plus n positive, we have that the omega g ends have poles only at the ramification points. Okay? Nice. So now we are ready to do the final proof. Hopefully, let's see how it goes. Okay, so the first thing that we want to use is just Cauchy formula, so something very easy. So we will just be using some tricks from complex geometry, but really elementary ones. So Cauchy tells us that we can write this as a residue at z equals z1. We add this simple pole, just because we want to recover this guy. And we just put this guy in here. Okay, but now it turns out that we are in a compact Riemann surface. So we have that the sum of residues of a one form has to be equal to 0. Right? This is another classical thing. So for any p in the Riemann surface, actually this will just contribute 4 poles, and there are finitely many poles, and this is a finite sum. The sum of residues is equal to 0. You probably use this trick even for exercises with in Bertrand's course. If this is a meromorphic one form. On the Riemann surface. Then from this, we can just look at the other poles of this thing. And the other poles, we just said this has no more poles. And we just said that this has only poles at plus and minus 1. So this is equal to the residues and plus and minus 1 of minus this. Okay? So we just take I'm just reversing the sign in the denominator. We just take this. Now we use something very easy. We just use that actually our ramification points have this property. So we can actually sum another term like this with 1 over z, and they will have the same residue, because we are taking residues at these points. Okay, so we can sum them and divide by 2. Okay, so we do this. And I still have one whiteboard, very nice. So now I want to use Q-symmetry. So, okay, just by Q-symmetry here, we will just be able to write this guy again like this, so with z, but we have to change the sign here. So this is just what I'm doing now. Yes. Yeah, it's fine. Okay. Sorry, I'm making a mess with the differentials. Yes. So, okay, we have the dz inside in here. So this was dz1. And here, where did the dz1 go? I just didn't write it. Okay. But now, observe that this thing is something very familiar. It's already, okay, maybe let me just not write the whole thing, but I will just write the thing inside the residue is just this integral of the Bergman kernel with respect to one variable of the Bergman kernel. Okay. Is it okay? Other questions? No? And now we need to use touch recursion, and it's a pity that it's not there in the Blackboard, but hopefully it's in someone's notes, or you can remember more or less the shape. So I want to substitute now this guy with the other thing on the side of the, so the right-hand side of the touch recursion. And we need to use, of course, that we have transformed in the touch recursion the functions to differentials according to this formula. Okay, so this is important. So this is what we will do. This is a bit awful to write. So yeah, maybe I will just write it and then try to justify everything. And unfortunately, it will not fit in here, because remember that the touch recursion has quite some terms. So, okay, this looks like this. You can maybe already start checking like all the signs and everything. if you have the touch recursion in front of you or remember the shape. So I'm putting here first the polynomial. I'm turning everything into differentials. Remember, this was the polynomial, so I have to add all the x's. Maybe I will not write more here because I will do manipulations on the formula later. Maybe it's nice to see this. But maybe this we don't need. Okay, maybe we can already make it fit not too badly in there. So there are more terms. So I'm using now this notation to mean Z2, Zn without Zi. Okay, is it big enough? You seem fine. And now here dx to the square, well, maybe. This is Z2, Zn, remember. Okay, these guys come from the differential term of the touch recursion, and then I'm adding the terms that will stay there, that are the topological recursion terms. So here I'm writing no disk, and it's because I removed the disk from there and I put it on the other side of the equality. Remember that in the touch recursion there was no disk. We also had that topology included. Okay. Yes. So, okay, let's comment a little bit. It's not so bad. We just substituted this guy by the WGN times dx1 dxn, and with these shifts for 0, 1, and 0, 2. Then used touch recursion. So remember that in touch recursion you had this type of guys, I was saying, but here you also had disks. So we took the disk term from the touch recursion, we put it on the other side, and we combined it with the term from touch recursion that had W and V prime. And because there is this combination, that gives you exactly the omega 0, 1 from the denominator in here. Yes, just remember that, well, you need to use also skew symmetry, so it's a bit tricky, but not too much. Hopefully. Remember that this is just equal to this. Okay? And then, well, maybe we also want to remember that this is equal to this. To know how many poles this has. Sorry if this is getting a bit too smashed. So which other subtleties are there? not many more. So there are some other subtleties that I'm completely putting under the carpet. So these guys I'm not treating at all. So for special topologies, I think 0, 3 and 1, 1, because it's where these guys will appear in here as accompanying the other one. We also have to treat those special things, but they will never contribute to the residue. So I'm not even writing them in this generic formula. Let's say that this formula is for generic D and N. If you have a small d and n's, there are some extra terms that you also need to eliminate. But okay, now I will eliminate all the terms that are not there, and we need to justify why. So at least I will do it for the generic case, and believe me that the other cases are easier. So if you are careful enough, you should be able to complete everything with the tricks that I'm going to show. So we have to change the signs, because we don't like this sign. So I will do it with red. Hopefully it's not too confusing for the online people. I'm just changing signs everywhere. So I want to turn this into a plus. Oh, sorry, not this one. So we will have a minus appearing here. What else do we want to do? We want to use skew symmetry in some places. And I was saying that this already looks a lot like topological recursion, but still we want that this is equal, and if I want to be consistent with the color, so everything is correct, picking the right color, of course, the right color with color. This guy, we just write it like this by skew symmetry. So we get exactly this guy that appears in topological recursion. Here we do exactly the same. So we are also rewriting this term over here as the same first guy, so the same sum, the same first guy, and in the second guy, well, it's not important at all that it's the second one, but in one of the guys, this will just be 1 over z. And just changes the sign. And again, we get exactly the term from topological recursion. So what do we have left? We just need to eliminate everything else. So let's do it. How to do this? So in here, we have to check which are the zeros, okay? Because we need to compute the residue, remember. So this has, oh, this blue is not, maybe not working very nicely, but if I do it in black, I think it's going to be terrible. So this guy has a simple a simple pole at z equals the ramification points, because this guy has a double pole, and we take the integral. Oh, sorry, no, this is not what I'm saying. I'm saying that this guy has a simple 0, just because of this integral. This guy will be equal to this guy, okay? So it's a simple 0. And now I'm talking about zeros at z equals plus and minus 1. So I will not write it all the time, okay? But this is what I mean by simple 0. Then where else do we have this type of things? Well, this guy has a double 0. Why? Because this guy has a 0 and this guy has a 0 as well. Okay? So this guy has a double. Okay, this is probably very bad. There's no hope to do it in blue. It's a double 0 at those guys, plus and minus 1. Then this term over here contains the x to the square. So it has a double zero at the ramification points. So since this has a double zero, this has a simple zero, and the denominator has a double zero, it will not contribute to the residue. Okay, because remember that the residue, we only want things that have a simple pole, right? So okay, this guy goes away. Maybe I just cross them with red. This term goes away. Then the next term, this one is a bit tricky. I think it's maybe the trickiest, but this one is very easy. It's just the same reason as before. This has a double zero. So this one doesn't contribute. And now for the other one, let me do it apart. Maybe I can do it here. Remember, we just need this one. When we have this one, when we are convinced that that one doesn't contribute, we already have the formula of the topological recursion. Okay, so remark. The kernel of the topological recursion I remember what the kernel is, but you see it already there. And so this is the topological recursion kernel, and from its shape, it's clear that we can change z to 1 over z, and it stays the same. Why? Because if we change z to 1 over z in the numerator, we just change the sign, and if we do it here, we also change the sign in both, so it's good. We have the same. And then, okay, I still need a big thing. Yeah, I was hoping to not have to remove this. Maybe I will just remove everything from here, but I will leave the beginning. So second part of the remark. Well, this guy, the residue of that guy is equal to 0. The residue of that guy times the recursion kernel is equal to 0. Why? Well, it's very easy, but let's do it. Times that guy. Okay, so we use the same trick as before. This is the same as changing, so the residue will be the same if we change z to 1 over z everywhere, but if we change z to 1 over z here and here, that stays the same. So the only thing that changes is this one. So we can take those two guys and take the half of it, and we will get what we want. So we get the thing that stays the same. And we get multiplied by this guy plus this guy with 1 over z, and the same in here. But now we know that this guy is Q-symmetric, so this is just equal to 0. So it's not even that it doesn't contribute to the residue. Well, it is, because we used the residue here. So this just gives 0 by Q-symmetry. And we finished. We are able to kill our last guy, our last non-topological recursional guy. So we just got the formula of topological recursion, which is this term and this term. the residue of the kernel in here is equal to omega gn. So we finished. Okay. Are there questions? No? Now I'm not very sure if you are all very tired or you are understanding everything. Probably the second one. Okay, so let's talk a little bit about our last part, the dual problem. So I will just start telling you about this general property or conjectural property of topological recursion, which is symplectic invariance, because I think Bertrand didn't really mention this. And this is one of our motivations, like understanding what the most complicated case of symplectic invariance means, which I think the full understanding of this is still open. So this was one of the motivations to define these fully simple maps. Not the only one. So now I call it like the dual problem of ordinary maps because of this reason, but also because of some other reasons. So it's an interesting phenomenon. So symplectic invariance of TR. Maybe I will just give you the simplified version because it's a bit late and probably you're all a bit tired. So if we take a spectral curve, okay, this is a bit simplified. I'm just taking the Riemann surface and x and y. We apply the topological recursion. We get the omega gns, and we get our fg's that were defined by Bertrand, and they are just the omega g0. They are numbers, well actually in the case of maps they are like rational functions on the t's. So they depend on the parameters on the moduli of the curve. They are not just complex numbers. But okay, in principle, morally they are numbers because they don't have x's. Then we take here a symplectic transformation. What do we mean by this? We just mean that we take a transformation of x and y that preserves dx wedge dy. Well, actually up to a sign if you want, to make it a bit simpler even. Then we get here like the same Riemann surface and the transformed thing that has the same wedge dx dy. We apply topological recursion, we get the omega gns that I call omega gn wedge. Okay, we get the wedge numbers. And what symplectic invariance tells us is that, in principle, these two numbers should be the same. Okay, and this is true for many symplectic transformations. So actually, for all of them that don't involve changing x and y. As you can imagine from the topological recursion procedure, exchanging x and y is a really cumbersome transformation. So it's already very interesting that there is actually something going on. This has many physical motivations, so maybe I will just not talk about this. I'm not going to justify that this is fine for the other transformations, but believe me that it's true. So for this one, the one that I call E from exchange, this is not well understood. So they are expected to be equal up to some corrections that are not very well understood. And actually, personally, I don't care too much right now about which are the specific corrections. I care more about understanding what is going on, what is the phenomenon that is going on. This has many physical motivations. Probably Bertrand can tell you much more about that. Like has to do with background independence. It has to do with the fact that exchanging x and y in the quantum curves makes some sense from the physical point of view. Has to do with many things, but it's quite surprising and quite strong. You can use it to prove strong things. Okay, now I promised that I would justify why I'm calling fully simple the dual problem of maps. Well, actually, if you just take the spectral curve of maps, so x, the x that we saw, y, well, let me call it w, but it's very related to the y. Or you can think it's just the y, to simplify a little bit. It's just the generating series of disks. We apply the topological recursion. We just proved. This is one of the problems that satisfies topological recursion from the origin of topological recursion. But we just proved in these lectures that this satisfies topological recursion if this is the generating series of maps. Okay, and now, what happens if we exchange x and y? Well, you can probably guess. One nice thing is that this result that I'm going to state now is now a theorem. It has a bit long history. At the beginning, it was proved using symplectic invariants, but not everything was justified there, so then it turned into a conjecture again. But now it's finally proved again, so hopefully it will not turn into a conjecture anymore. And it just tells us that if we take the curve exchanging x and y, we apply the topological recursion, we get the wedged omega gns. We have to divide by the coordinate associated now to the new x. Here we get fully simple maps. This is the generating series of fully simple maps that I wrote yesterday. Okay, S stands for fully simple. Okay, so this is quite nice. But let me tell you what happens. Okay, what are the base cases of this theorem? And then maybe a nice exercise, if you want to understand a bit how these combinatorial maps work, is play with these base cases, because they are easy to prove. I mean, disks is easy to prove from combinatorial transformations. Cylinders is already not so easy. But okay, disks is actually a nice exercise, so maybe we can propose it as an exercise for tomorrow. These two generating series of fully simple disks and of disks, are inverses of each other, which looks a bit surprising because fully simple disks are like many less than disks, but they are inverses of each other. So this was the first phenomenon that we observed and that told us that this is probably an interesting problem, because maybe there is a chance that this is the problem that goes in here if you exchange x and y. And also, this is some important formula that you find in something called free probability, which is some well, in free probability, you take the notion of classical independence of random variables, you turn it into something called freeness, and this freeness is especially well suited to study non-commutative probability spaces. This is in very few words, more or less, what free probability is about. And in free probability, you find this formula that is very important. So it also told us, okay, maybe this has to do something with this nice phenomenon from free probability. So now, if we set xi to be just this guy, we can write what happens for cylinders. And you get also formulas from free probability that actually people in free probability were very surprised to see that with the intuition from topological recursion, this has a kind of obvious way of writing them in this symmetric way. They thought it was impossible to write their formulas in a symmetric way, but this is Bertrand's tricks of writing everything with differentials, and things get more natural. So this is just the formula that you get. These two things are the same, and of course this is something that we wanted to even be able to state the conjecture, because this is the base case for disks. Because, as I told before, the Bergman kernel is a universal object. Sorry. And you get here that in the z variable, so if you take the axis that we showed before, this is just the Bergman kernel in both cases. Oh, sorry, maybe you were saying that you cannot see here? Okay. So I just wrote that this is equal to the Bergman kernel. In both cases, and with the right coordinates. So again, from the same Bergman kernel, if you have the right transformation for the x, you can extract very different numbers, ordinary cylinders and ordinary fully simple cylinders. Okay? And now I can just sketch the relation, how to relate one problem to the other using Hurwitz numbers. So it's very convenient that we had Danilo's lecture before mine, because now I can use the power of Hurwitz numbers without having to define them. Yeah, sorry.
I wanted to ask, the fact that B is the same for the two sides, so you're making use of that fact to extract x02, right? But is that itself a fact that is obvious, that B has to be the same for two sides, or is that something we have to show?
Not at all. It's not obvious at all. It's what we wanted to show. Actually, so the fact that this is equal to the Bergman kernel is what is shown for the ordinary cases that I explained, no? So we wanted, our intuition was telling us that for this problem, if you take the same kind of expression, but with the other problem, so with the other variable and with the other generating series, here we should get the same Bergman kernel for the z's. This is what we wanted to prove. So actually I am writing this equality, but we wanted to prove that this is equal to this. Because then, really, when you exchange x and y here, everything makes sense. You get here the usual Bergman kernel for CP1, and you get here the usual Bergman kernel for CP1. So it's crazy that the Bergman kernel is the same, just for completely different problems. And of course, to extract the same numbers, you have to change the meaning of the things. You change the meaning of the generating series, and you change what this guy is. This is topological recursion. Here you're changing 0, 1, and here you're changing the meaning of what you want to count. But in the z variable, they have the same shape.
So I just want to know what fact is used to find what fact. So we use the fact that B is the same to find what is x02, or we compute x02 X02 and show that B is the same? I mean, what follows from what?
Yes. So I guess this is what we wanted to prove, this equality. And to prove it, we decompose ordinary maps into fully simple pieces combinatorially, and we show this equality. And since we know that this is equal for ordinary to this, then we show that this is equal to this, and we prove what we wanted. But yeah, thank you for the questions. This is actually something very surprising, so it's nice to comment on it. So Hurwitz numbers. So remember from Danilo's lecture that this is the conjugacy class in GL, where L is the size of the partition. So it's just the sum over all parts of this partition. This was denoted like partition of L in Danilo's talk. Just to remember some notations. Okay, so this is the conjugacy class of cycle type lambda inside the symmetric group on L elements. Okay, then we define, but I'm gonna rely on the fact that you already know about this a little bit. We define double Hurwitz numbers. You saw in Danilo's talk, I think, simple Hurwitz numbers. Now we want to fix two ramification profiles. So we are just defining this as the number of covers in which we fix two ramification profiles, the ramification profile over 0 and over infinity. The 1 over 0 is given by lambda. The 1 over infinity is given by mu. Here we will have some genus that we know how to compute. Well, even some connected components, because this is disconnected. And well, this is just the number of these coverings, the ramified coverings of the sphere, and we also allow simple ramifications in other points. And we know how many of the simple ramifications are. They are all related by the Riemann-Hurwitz formula that Danilo presented. There are k of them. So we can also count this using the symmetric group, as you also saw in Danilo's talk. So this is just the same as the tuples of permutations. We take sigma to be of cycle type given by lambda. We take the tau i's of V being just transpositions, so of cycle type 2, 1, 1, 1, 1. And we take that the product of these guys has to be of cycle type mu. Okay, so this is the definition of Hurwitz numbers. There are also some automorphisms that I'm not going to talk about at all. But remember, then I can state the theorem and we can finish here. So the theorem will tell us how these two problems are related. This is the bad one. Via Hurwitz numbers. Maybe tomorrow we can, whoever feels like, can deduce some things from this relation. But the fact that these two problems can be related with these Hurwitz numbers is also what is making me right now call them dual problems. Related to other things that I'm not really going to discuss, but okay. Okay, so I have to say, that's why I said that they are also this. I have to say what I mean. Just briefly, if we write the transpositions like this, and we have that the BI are increasing, but weakly increasing, then we call this weakly monotone, and we denote them just like this. And if it's strictly, then it's strictly monotone, and we denote them just with a strictly smaller or equal sign. So we just need this guy, and then I'm able to state the theorem and finish here. This is just L factorial over the number of guys in that conjugacy class. The theorem tells us that you can go from one problem to the other using these two problems, these two Hurwitz problems. So, generating series of maps of fixed lengths given by a partition lambda. And we are treating the disconnected case because the formula is nicer. We need this z, this zeta that I defined here. There is just some kind of automorphism factor. And we take the sum over partitions. We take the sum over all possible k's, n to the minus k. Remember that n was this guy that was kind of adjusting the topology. Here we find strictly monotone Hurwitz numbers. And on the other side, we arrive to fully simple numbers. And the opposite formula, you can, once you find one, you can find the other one very easily if you understand how the Hurwitz problems are related. Naturally, nowadays there are 3 proofs of this theorem, and each proof gives us different information. Or at least there are combinatorial proofs of the first guy, because you don't have any minus sign, and when you don't have minus signs, you do combinatorics. You can do bijective combinatorics and prove this, but this is not how we discovered the relation. We discovered it with the second one using matrix models and the power of Weingarten calculus that helps us compute unitary moments of unitary, so moments over the unitary matrices. And here on the other side, we find ordinary maps. So, okay, let's just repeat the idea. We can go from ordinary maps to fully simple maps using strictly monotone Hurwitz numbers, and the other way around, from fully simple to ordinary using weakly monotone Hurwitz numbers. Yes. Well, thank you. So, are there questions?
So, when are you giving your exercise session?
The exercise session will be tomorrow.
Yeah. What
Yeah.
time?
Tomorrow and at the beginning of the day, so the first
Okay.
lecture in the morning.
So, thank you, Elba.
Thank you
Thank
for
you.
listening.
Bye-bye.